Okay, let's have a look at our binomial theorem. So binomial expansions, which I guess you've been doing for a while, all it really is, it's an expression with two terms. That's a binomial. So to expand them out, we then raise them to some power. So 1 plus x to the power of 0, I guess, would be the simplest binomial. And of course, anything to the power of 0 is 1. And then to the power of 1, we get 1 plus 1x. 1 plus x all squared, we get 1 plus 2x plus 1x squared. And I can keep going. 1 plus x all cubed ends up being 1 plus 3x squared plus x cubed. And 1x to the power of 4, if we were to expand that one out. 1 plus 4x plus 6x squared plus 4x cubed plus x to the 4. And so on and so on. And you see that there is a pattern. Blaise Pascal saw a pattern which we now call Pascal's Triangle. Truth be known, it was discovered way before Pascal. Like they found ancient Chinese scripts where they've been using these and so on. Pascal probably gets the credit because he's come up with a lot of different relationships that he found inside the triangle. So it starts at the top at 1, and then to get the next row, we add the numbers immediately above it. So 1 plus nothing is 1. But then the next row, we get 1 plus 1 is 2, and now we can keep going. Look at that, 1, 3, 3, 1. 1, 4, 6, 4, 1. And then we keep adding, 1, 5, 10, 10, 5, 1. That's a nice one. And then 1, 6, 15, 20. Oh, that's sort of nice too. I like that one. 7, 21, 35, 35, 21, 7, 1. We'll keep going. 8, 28. Oh, look at that. Lovely. You see the symmetry of it. 9, 36, 34. Oh, 126. Now, if I'm not, here it comes. Watch out for this one. You're going to love this one. Look at this. 110, 45. Look at 122, 10, 252. Look, 122, 10. Then you get a palindrome in the middle of 252, 210. Well, that has got to be the best row in Pascal's Triangle, in my opinion. Okay. So, if we want to expand out something like this, we don't have to physically expand the whole thing out. We know what the coefficients are going to be using Pascal's Triangle. We could look at the 7th row, and I know the coefficients would go 1, 7, 21, 35, 35, 21, 7, 1. And then it's just a matter of, okay, the first one starts at the power of 7, and then its powers go down by 1, and the other one's powers go up. The two powers always add up to give 7. There's our expansion. Turns out, if we tidy it up, to be that beautiful thing right there. Okay. But where it's really handy is something like this. Imagine you're out shopping or something, and someone comes up to you and says, "Excuse me, could you tell me what 0.998 to the power of 10 is?" To 8 decimal places. And you haven't got your calculator on you. Okay. Bit embarrassing. But what you could do is you can go, hang on a sec, 1 minus x to the power of 10. 10 is that great row, so we'll remember the coefficients. That's not a problem. And we could rewrite, so there's the expansion, 1, 10, 45, 1, 122, 10, 252. Powers of 1, well, anything to the power of 1 is 1, so I don't have to worry about that. So basically the powers of x are just going up by 1. Because it's a minus, it'll alternate, plus, minus, plus, minus, plus, minus. So very easy expansion. And 0.998, of course, is 1 minus 0.002. But I stopped at cubed because they only said to 8 decimal places. So once I get to the power of 4, to 8 decimal places, 0.002 to the power of 4 is 0. So I know I just have these. So I can save my embarrassment at the shops. I just got to work this out in my head. That's easy. No, look, 2 squared's 4, 2 cubes 8. So you just do a little bit of mental arithmetic and go, oh yeah, no worries. That's 0.980179004, and you save all your embarrassment. Thank you, binomial theorem. Who says maths isn't handy? Ooh, blank. Okay. Now, if we want to find the coefficient again, I don't want to expand the whole thing out. I mean, clearly, if I expanded the whole thing out, I could find the coefficient of x squared. That's time consuming. Okay? But if I did, here it is. And I'd expand the whole thing out. But really, I don't want to expand the whole thing out. All I want are the things that come up with x squared. So I know the 2 would have to be multiplied by the term in the second parentheses that would have x squared. So as I say, I don't have to expand the whole thing out. If I know that the term with x squared, its coefficient is 6, the two powers have to add up to be 2, so the 4 must be squared as well. And then I could do a similar thing with the 3x. It must be multiplied by the term that has x in it. So 4 must be to the power of 3, because powers add up to give 4. And I just look at those two terms, and they turn out to be 960. So I don't have to expand the whole thing out. I'm only interested in the terms that will produce x squared. Okay, 5A.